Hey, let's talk vectors. A vector is a real simple idea that we use a whole lot in physics. It has to do with any quantity that has a magnitude and a direction. Magnitude is a fancy word for number, and direction, of course, it points in some direction. So if you're going down the highway 70 miles an hour north, the 70 miles an hour would be the magnitude, and the north would be the direction. You'd have both parts, therefore that would be a vector. When we think about vectors, it always has those two parts, the magnitude and the direction. Now you could think of anything that you want here, but again, this is going to be some kind of number, some kind of measurement. The direction will be some kind of direction, all right? So we've already talked about velocity being an example of a vector. Position or displacement is also a vector. How far away from home am I? Did I end up 16 steps? That would be my magnitude. North of where I started or south? You know, what's the direction? If you've got these two, you got yourself a vector. We usually draw an arrow to represent that, and the length of the arrow could represent the magnitude of the vector, and the direction, of course, is pointed by the arrow. So maybe this is vector A right here. It doesn't really matter what it represents. We can just kind of give it a name. If it were a velocity vector, we'd probably call it V, and the displacement vector would be an X. Acceleration is a vector quantity. So that could go down here. Force, which way I push on an object, how hard I push, and which direction. F, A, whatever the thing is. But to mark this as a vector, to indicate that it's a vector, we put a little arrow on top of it like that. This would be V. As soon as you put that on, that's vector V, and vector X, the displacement vector, the acceleration vector, the force vector, torque, angular momentum. There's a bajillion of these things that we use in physics. The nice thing is they all work the same way. They have the same mathematics and the same behavior, and it doesn't really matter if we're talking about a force or an acceleration or whatever. So I won't dwell too much on that from here on out. But it kind of makes sense, right? If I walk, you know, from here to there, then I could record how far I went and in what direction. Or if I were the velocity, or if I were pushing this way or something, I would need to specify both parts of that. Now, before we get too deep into this, we need to either remind ourselves of some right triangle trigonometry or knuckle down and learn some right triangle trigonometry. In either case, it's not hard. If you've seen this before, that's fantastic. And if you haven't, that's okay. We're going to do it right here, right now. The rules that I need you to know about are right here on the right-hand side of the screen. There are 4 tricks that we can pull anytime we see a triangle. Now, this is a right triangle, so the right talks about this little rectangle right there. Anytime you see that little corner, you know you've got yourself a right triangle. Here's the triangle, and I got a right angle in the corner, so that would be a right triangle. And these 4 tricks work for all right triangles. I guess we should say on the plane, but that's probably not necessary what we're doing. But this is referred to as the Pythagorean theorem. You probably came across that back, I don't know where they teach it now, 6th grade, maybe somewhere back there. C squared equals A squared plus B squared. You remember that you do have to name the sides of your triangle, and specifically here, C had to be this longest side that's directly opposite the 90-degree angle. If this is my right angle, my 90-degree, then straight across from that is the longest side. It even had a name. That was the hypotenuse. I think it's U and then the E. That's the hardest part of right triangle trigonometry, is trying to remember how to spell hypotenuse. I think it looks like that. And then you had these 2 legs, and either one of them could be A or B. It didn't really matter. I'll put A here and B there, but it could be the other way. Those did not have names when we did geometry and Pythagorean theorem, and really the Pythagorean theorem comes from geometry. It's an important idea that tells us the ratio of these sides. And if I went and I took this triangle and I put it on the copy machine and blew it up to 2 times, 3 times, 6 times bigger than it started, it would still have the same ratio of sides. And if I knew 2 of those, then I could find the third one. So it's super easy to use. The world's most famous right triangle has got to be the 3, 4, 5 triangle. So if I measure off 3 feet or 3 inches or whatever, and 4 inches and 5 inches, that will make a right triangle. Okay, 3, 4, 5 triangle. That's how they got the pyramids of Egypt so straight and perfectly square and everything. They knew this trick way, way back. The ancient Greeks, the ancient Egyptians knew all about the Pythagorean theorem, and we should too. All right, so it's up there at the top. Notice that it's real easy to use. Let's say that we knew this side and this side. If I wanted to do the Pythagorean theorem, then I could come in here and I say, well, this side C, I know it's 5, but let's calculate what it should be, is equal to A squared, so that would be 4 squared, plus B, that's 3, it's squared, and I'd get 16 plus 9, and that's 25. So C squared is equal to 25. I'm looking for C. I need to take the square root of both sides. And so C would be 5. And there's my 3, 4, 5 right there. Okay? It works that way. They give you 2 sides. You find the third one. No big deal. All right? These other 3, maybe you've seen them, maybe you haven't. But they're the sine, the cosine, and the tangent. And these 3 are on your calculator. When you look at a calculator, right there, sine, cosine, and tangent, we abbreviate them down to 3 letters just to make it easy to fit on the button, I guess, because we don't want to write it over and over, I guess. But that's what we're talking about, and that's what we need to learn how to do here. If you've never seen it, that's fine. Every one of them has some kind of angle, and we call this angle theta. All right? That circle with the line through the middle is the Greek letter theta, and that's going to be the angle of interest. So one of these angles they're going to give you, and it's not the right angle because all the triangles have a right angle in them, but all the right triangles do. But let's say that they give you this angle right there, and they say that angle is 30 degrees. Now it's not going to be a 30-degree angle with a 3, 4, 5, all right? So I think it's more like a 27 or something, I forget. But I'm going to put let's just put 27 here, and I don't think that's quite right. But if they gave you that angle and said that's your angle right there, then you'd say, well, great, that's theta, all right? That would be the angle of interest. I'm interested in it because they gave it to me, and I'm going to have to do something with it, or because they gave me some other numbers and they want me to calculate that angle and find out what it is. Trigonometry, the measurement of triangles. So we're going to take this little bit of information that we have. Triangle is what we usually call it. That'd be a 3-sided, a trigon. But triangle is what I was trying to write. So let me do a little bit better there. If I can. Triangle. Man, they got to fix that. That's just all there is to it. Triangle. Okay. So there is the triangle measurement is trigonometry. We got 4 tricks. The first one's Pythagorean theorem. That's easy. As soon as they start talking about this theta, though, then we're in for sine, cosine, tangent. And this is even easier than the Pythagorean theorem, probably. What I need to do is to label all the sides. We've already got the hypotenuse right there, so that's no big deal. But the opposite and the adjacent are the other 2 sides. Keep the hypotenuse, add 2 more. If this is the angle of interest, then the opposite is opposite that angle of interest. It's straight across. So I'm going to just put OPP right there for the opposite side. Here's the angle. Opposite that angle is the opposite. And adjacent to it, or right next to it, is the side that we call the adjacent. Okay? So these trig functions, the sine of the angle is equal to the opposite over the hypotenuse, simply means that here's my angle, and if I take the length of this side and divide by the length of this side, that would be 3 over 5. That's going to lock in this angle right there. I only have one choice for an angle in a right triangle that will have a 3 here and a 5 there. It's got to be whatever that is, and I probably should have looked up that number and had that ready for you. But we can actually do it real quick here. Our process probably won't make much sense at the moment, but 3/5, take the arc tangent, 30.96. All right, so actually it's a little bit more than I was thinking. All right, that's okay. But whatever this angle is, there's only one angle that will fit right there with 3 opposite and 5 for an adjacent. Okay? So that's that. The cosine right here takes the adjacent divided by the hypotenuse. The length of the adjacent is 4. The length of the hypotenuse is 5. When you take 4 divided by 5, you get 0.8. And I'm looking for this trig function that has a value of 0.8. And when you solve it, that's called the cosine. All right? The tangent at the bottom there is opposite over adjacent. So basically you're taking the 3 sides and you are seeing what you want to do there with it. Think about what would happen if I took that triangle and I put it on a copy machine, and I made it, I was going to say twice as big, but I can't get a triangle twice as big there, so let's make it half as big, although that might make the numbers funny, but we'll come in right here, all right, and pretend that that's exactly half of the size and everything. Can you kind of see that the ratio of the sides are going to have to be the same? I'd have half the size there, 1.5. Half of 5 would be 2.5. Half of 4 would be 2. And the ratio, 1.5 divided by 2, is going to be the same number as 3 over 4. And so it's the ratio of the sides and how that interacts with this angle, theta, the angle of interest. All right? Now, sometimes we need to go use trigonometry to go one way or the other. If I wanted to walk from right here to right here, I'm walking path A. There's 2 ways to describe how to get from the starting point right here to the ending point right here. I could either tell somebody go 5 miles at an angle of 30.96, and that would get them there. Vector A could be written, go 5 miles at an angle of 36, what did I say it was? 30.96, I think was the number. Okay, whatever the number is, all right? 30.96, messed that up pretty good. That would get them there. You walk 5 miles at that angle, you're going to end up at the final point there. All right? But what I also could do, remember this was 4 and this was 3, so I could also tell them, well, you could get to that same ending point if you went 4 in the x direction, or 4 east, and then you went 3 in the y direction. Or, if you want to write it the other way, 4 east plus 3 north. And when I walked 4 miles to the east and 3 miles north, I would end up right there at that same point. So I could write it that way. Now, we don't write it either one of those ways in physics. We like this one okay, fine. So I'll put a circle around that one. But the way we usually, this is a lot to write. So we need a shorthand. We need an abbreviation. And the abbreviation that we do is 4i hat plus 3j hat. Okay, and that looks kind of funny mysterious even, whatever. But as long as you're okay with the idea that I hat is a little signpost, it's a little director that says that way, and J hat is a little sign that says, okay, now turn and go north, then you're fine, okay? I hat is what we call a unit vector, so I would go 4 to the east plus 3 to the north. All right, and that's all it means. So one of those two ways is the way that they would probably write that vector down, and you could get there either way. It's not the same distance either way, right? If I walk 4 and 3, it's 7, whereas if I just walk the hypotenuse, it's 5. But that goes back to the triangle inequality and theorems of geometry and all that. So that's fine. These polar and rectangular coordinates, those reference these two different ways to write these things. This would be polar coordinates in the first example up there, and this would be rectangular coordinates down here. All right, so that is what we're trying to do with that. All right, now it is possible if you have one to get the other one, and in this case we're going from polar to rectangular. On the next screen we'll go from rectangular to polar, and so I want you to see how to get back and forth between these things. The answer is with trigonometry. All right, if we use those rules of right triangle trigonometry, then we're good to go, and we can convert these things back and forth with no trouble. So I'm going to draw this triangle again, just with the numbers that we need. I put a whole bunch of mess on there. That's vector A, and it's 5 at an angle of 30.96 or whatever. We'll find out how close that angle is, all right? But I want to go to the rectangular. That's the polar. I want to go to the rectangular. I want to know the east and north parts. So I'm looking for this line right there. That would be the x component of A. And since that's a lot to write, we usually just write A sub x, like that. And then I want to turn and find the y component of A. Vector A. And again, that's going to be A with a little y here to say just go get that piece of it. I want to know how far to the right and how far up. How far in the x direction, how far in the y direction, how far east, north. However you want to think about that is fine. But that's what we're trying to do. And I'm going to take this angle, since they gave us that, and I'm going to put it right here. If I can get this thing going. And because that's kind of a 30.96 right there. All right. If that's my angle of interest, the y component would be the opposite. The x component would be the adjacent. And the hypotenuse would be this side, the longest one across from the right angle, which is here. Okay. Now you always have to name those sides, and you always need to look and see which side is it that I'm talking about. If I had changed the angle, for example, if all of a sudden they gave me this angle, now the opposite would be straight across. This would be the opposite, and this would be the adjacent. So if they switch the angle, then the names change, which of course mean that the trig functions change. All right, so always draw out your triangle and label those sides opposite, adjacent, hypotenuse, and then just do the trig function and see what it's supposed to do. I'm going to put the trig functions here again. You should know these. They could be on your index card if you want. Sine theta equals opposite over hypotenuse. There's my first definition. The cosine of theta is always the adjacent over the hypotenuse. And we have the tangent. We don't really need the tangent here, but I'm going to put it anyway. Opposite over adjacent. Okay? So now that I know, let's see what we know. I know the hypotenuse. That was 5. Okay? Right there. Not going to do it. And I also know theta. I want the adjacent. When I want to know the x component, see how here's hypotenuse and adjacent? This is like we did kinematics. We figured out what we knew and what we wanted and found a formula that linked all that together. In this case, if I have the hypotenuse and theta and I want the adjacent, and I come over here to my list of possibilities and look for something that has hypotenuse, theta, and adjacent. Well, they all have theta, so don't worry about that. The one that has adjacent hypotenuse would be cosine. So that's the trig function that I want to use. And I would say cosine theta equals adjacent over hypotenuse. I'm looking for the adjacent, so I want to get rid of that divided by hypotenuse. Let's just multiply both sides by the hypotenuse, and I'll have the length of the adjacent, and I'm interested in that because that is a sub x. And so right here, my magnitude of the hypotenuse was 5 times the cosine of 30.96. That is a sub x, and my calculator knows what to do with that. I want to scare you into paying attention to this here. If I do 5 cosine 30.96, I got to turn it on first. 5 cosine 30.96. That's going to give me an answer 4.29. All right, I don't know that I did something right here. Anyway, 4.28 is what I would get for that. Oh, I see what I did. I put 3 over 5. It should have been 3 over 4 before. So I've got my angle messed up here. All right. It's not going to be a 345. All right. It's going to be a 4.29, something like that. All right. Anyway, 5 times cosine 30.96, this would be 4.29. That is my x component right there. And then I can start over again. I really, now I've got two sides of a right triangle. I could use the Pythagorean theorem, but we're trying to talk about sine, cosine, tangent. So let's do it that way. And I'll come in over here, and now we see that I know the hypotenuse and theta, and I want the opposite. I want the y component. So I'm looking for something that has opposite and hypotenuse. That, of course, would be sine. So sine theta equals opposite over hypotenuse. Multiply both sides by the hypotenuse because I want the opposite by itself. Like that. And here's a 5 times the sine of 30.96. That would be my opposite. I'm going to call that a sub y now. That's that vertical component, that piece right there that points upward. Tells me how far that vector reaches up. And my calculator says that that is 5 sine 30.96 is 2.57, somewhere in that ballpark. All right, round it off somewhere. Okay. So that's kind of neat. I could now take the x component and the y component, and I could write this vector. Initially, we said that A was 5 at an angle of 30.96. That's the polar representation of it. Give me the length and the angle. You got polar. I want the rectangular. So A is equal to 4.29 in the x direction, I hat, plus 2.57 j hat in the y direction. There's my x direction, y. I found them over here, and I can just put them in. Either one of those will get me to the right place. You can see it's not a 3, 4, 5 triangle because I messed up and used the wrong number somewhere. But that is what we're trying to do with this thing right there. And we just changed from polar to rectangular. And that wasn't too hard at all. You got cosine and sine. All right. We can do some more of those in class. If that doesn't make sense, please ask questions. Let's get it right. All right. But here's going the other way. Let's say that we have rectangular and we want to go to polar. Why don't we do 3, 4, 5 here just to make the numbers a little bit easier. If I let this be a 4 and this one be a 3, and I want to know how far this reaches, and I want to know what angle I get right here, then we could do that. All right. Remember, we had 4 rules. One of them was the Pythagorean theorem, so this would be a real good place to use the Pythagorean theorem. I have 2 sides of the right triangle. I want the third one. So I could come in here and say A, the length of that side is equal to the square root of A sub x squared plus A sub y squared. All right. Pythagorean theorem, like we wrote it the first time, was C squared equals A squared plus B squared. So all I've really done here is gone ahead and taken the square root of both sides and then just replaced A with A sub x and B with A sub y, just to get it in the names of the sides of this triangle instead of a generic triangle. All right, but this is easy because all I got to do is put in the numbers here. A sub x is 4, A sub y is 3. I come down here. This would be 16 plus 9 is 25. Square root of 25 is 5. All right, so that's my magnitude. That would be the length of that thing. And I'd like to know the angle as well. So to find theta, I have to pull this funny little trick. Notice, let's name our sides here. We probably should have done that to begin with. Hypotenuse is always the longest side. Here is my angle of interest, theta. Straight across would be the opposite. Right next to it is the adjacent. So if I know the opposite is 3 and the adjacent is 4, and I'm looking for a trig function that uses opposite and adjacent, I am drawn to this one. The tangent of theta equals opposite over adjacent. Like that. And I know the opposite and the adjacent. I could go ahead and fill those in if I want. Like so. But I got to get this guy by himself. So we do this funny little thing here where we slip tangent to the other side and put a mark to say it was over there and now it's over here. It looks like this. Theta equals the arctangent of 3 over 4. Okay? That's the arctangent. And what you're essentially saying is, go get me the angle when the opposite is 3 and the adjacent is 4. Well, your calculator's happy to do that for you too. Right there is my tangent button. So this is that tangent to the -1 or the arctangent. Sometimes people call it the inverse tangent. I don't really like that name because we didn't invert anything, right? It's not an inverse at all. It's just looking for an angle. But if I hit second tangent, I get, there's tangent to the -1 just like I want. And then all I got to do is 3 divided by 4. And that's a 36.9 degree angle right there. Okay, so now we started off with this thing. Vector A is 4i hat, 4 in the x direction, plus 3j hat, and now we've changed that. Still gets us to the same point, starts at the same point, ends up at the same point, takes the same path, but we've got go 5 at an angle of 36.9 degrees. All right, so there's 2 ways there to do that. This would be the rectangular. This is the polar right beneath it. All right, so we got those. Now I should show you here on the calculator. I think I've talked about this on the math review video, but there is a setting on the mode button that says radian. And if you get the blinky thing on radian, or if your calculator starts out in radians and you do the same calculation, you're going to get a very different answer. Okay? This is the angle in radians. That's the one in degrees. If I say 5 sine 42, and I do it in radians, I get that number. If I put it back to degrees, I get a different number. Okay? They're both right, but they're using different units. and you need to know which unit you're in, we will always work in degrees. Okay, we'll do some radian stuff, but we're not going to do sine, cosine, and tangent of radian. So just set it to degrees and leave it there unless you've got trig class or something else, and then just always switch back and forth and make sure you know which one you're in. Okay, that's the easiest way to mess up everything right there. All right. So just real quick, here is the summary of this thing. If I want to go from rectangular to polar, then what I need to do is to say my vector, let me put an A there, and you could change it to anything you want, but I would have the length of that, like we just did, is going to be the square root of a sub x squared plus a sub y squared. You could put that on your card and say anytime I need to go from a sub x and a sub y and get a and theta, I know I got to do the Pythagorean theorem, and then I got to do the arctangent. And since arctangent is opposite over adjacent, I've got to make sure to get the a sub y over the a sub x. All right. On the other hand, if you wanted to go from polar to rectangular, that's pretty easy to do too. The a sub x we wrote was a times the cosine of theta, and a sub y is a times the sine of theta. All right. So those four little tricks there will keep you in good stead anytime you need to do that. Of course, you do have to know which is the angle of interest and name the sides appropriately. If this is theta, then the opposite and the adjacent, you know, and just make sure you know which ones are which, and always work off of that definition of sine. Now, the last thing I want to do here on this video today is to add some vectors. And with what we've just done, you can see this shouldn't be too hard. Let's say I walk path A, and then I walk path B. I turn and change my direction, but R goes from the start to the end of this thing. I started right here, and I walked up there, and then I turned and walked up to here. I ended up right there. We want to give somebody the polar coordinates to go all the way to the start to the end, not following A and B, just following the red line. I've got a little four-step process here that does this, and it's real easy to do. So let me just show you real quick what it is that we want to do. There's 4 steps to this thing. Let me start way up here just to make sure I got enough room. Step 1 is to find r sub x, and to do that, all I got to do is a cosine the first angle plus b times the cosine of its angle. And what happens when we're doing that, we're adding these two things. A cosine theta A would be the x component of A. See how A takes us to the right, and then B takes us a little farther to the right? Well, if I were to add those two pieces, that would get me the total distance to the right. Like there, that would be r sub x. And it would be made up of a sub x and b sub x. So that's what we're doing right there. This much would be a sub x. This would be b sub x. We get those two x components, we add them together, and we get the total distance to the right or left, depending on which way the vectors point. All right. So since I've got a here is 20, that would be the magnitude. And here's the angle 35, like that. Then it's really easy to just put those numbers in up here. So this would be 20 cosine 35 plus, and over here b is 15 at 55. So I'm going to put those numbers in. And I'm using cosine in both of those. And I grab my calculator and I see what that is. I'm going to check, make sure I'm in degrees. I am. And then I would go 20 cosine 35 plus, uh-oh, I messed up right there. Check what happens. This is not quite right. See how it's taking the cosine of 35 and that parenthesis got opened? It's still taking the cosine of all of that. So be real careful. That is a number, it's not the right number. What you need to do is 20 cosine 35 and close the parenthesis. You're done taking that first cosine, so close it off. And then go plus 15 cosine 55. You can close that one if you want. There's nothing after it, so it doesn't really matter. I'll go ahead and put it. But 24.98, I'm going to just put 25. That's close enough, right? But see how the 14 and a half is nowhere close? So always close those things off. There's my 25. And that's step 1. All right. Step 2 is very similar, except now I want to find the height of this one and add the height of this one. This would be a sub y, and this would be b sub y. And when I add those together, I'm going to get the total height. Like that. Okay? So that would be step 2. And we do it almost exactly the same way. The only difference is now I need the opposites. And from what we just wrote down, the opposite, I use sine. So this is step 2. All right, let me go back to that last screen. The y component, sine, the x component, cosine. See how that matches up with what we had right here? The x component is cosine, the y component is sine. So unless they go and flip the angle on you, you're kind of safe just always doing it this way. And again, all you got to do is put the numbers in. This would be 20 sine 35 plus 15 sine 55, and you punch that in. So I'd come in here and I'd go 20 sine 35, close it up, plus 15 sine 55. And that's a 23.75. I'll call it 23.8. All right? Something like that. So what we've done is we've effectively made a new triangle. We said here is a triangle. Here's that red sign R. R, incidentally, stands for the resultant. It is the result of all this moving around. The result of following A and B is the resultant, the R there. And so vector R goes that way. And now I know that the x component down here is 25. And this is 23.8. And since I have two sides of a right triangle, it doesn't want to let me put in the right triangle right there, but ha! I tricked it. I can come through and do step 3 and do the Pythagorean theorem. And I just use these two numbers as the, I got 25, don't forget to square it, 23.8, square that. And so the length of R, by the Pythagorean theorem, second square root 25 squared plus 23.8 squared is going to be 34.5. We just found out how long this side is. I guess we could have put it here. That would have made more sense. Okay, if I walk 25 miles this way and 24 miles that way, I didn't go 49 miles. I'm 34.5 miles away from home. And I shouldn't have put the degree mark on there. Okay, maybe this isn't distance at all. Maybe it's velocity. Maybe I'm in a boat going 25 miles per hour this way, and the wind's pushing me 23.8 miles per hour that way. I'm really going 34.5 at that angle. And we'd like to know what that angle is. So I need that angle theta in there. So that's where step 4 comes in. And like we just did, we can get that using the arctangent. Now I'm going to give it a different name here for a second. Let's call it phi. The arctangent, tangent is opposite over adjacent. The opposite side would be r sub y over r sub x. So that would be the arctangent of the opposite, 23.8. You want to use the second number that you cooked up. The answer for step number 2, 23.8, and divide that for the answer by from step 1 would look like that. And your calculator will chew that up real quick. Second tangent, 23.8 divided by 25 would be 43.6. Okay? So that's that angle. I don't have to do anything too funny here, so I'm going to just switch that back to theta. That would be my angle. That's my direction. Here's my magnitude. And I could now write that r equals 34.5 for the magnitude at an angle of 43.6 degrees. And that would be a perfectly fine way. That would be the polar notation way to write that. I could also do it in rectangular. Since I've got r sub x and r sub y, I could also say that r equals 25i hat plus 23.8 j hat. Okay, and that would be the rectangular way to do it. But since they gave me these vectors in polar, they probably want them back in polar. So I'd do steps 3 and 4 and fix that up. All right. Now, that's the gory details of that. Once you've done it a couple times, it becomes pretty easy. Here's a little summary. And so you may want to make some kind of note on your card. You see here they've done it with 3 vectors. I can add 3 vectors at the same time, or 15 vectors at the same time. You're going to use cosine for the first step, so I'm going to just put a cosine theta sub a plus b cosine theta sub b plus dot dot dot. If you had 15, you just keep going. Use cosine on all of them. And you're just grabbing this number, cosine this number, plus this number, cosine that number, plus this number, cosine that, just until you run out of vectors. All right? Second step is always going to be sine. And again, just keep going until you're out of vectors. Plus dot, dot, dot. Right here, now that I've got the adjacent and the opposite, I could use those in the Pythagorean theorem. And I'm down to 2 answers. I'm using the answer to this and the answer to that and putting them in there. And so that'll give me that. Right here, it's always second tan, arctan of r sub y over r sub x. Okay? And there's this little thing down at the bottom, fix it if you get a negative number anywhere. And I'll have to show you how to do that. But that should always work. That is the summary there. And we'll talk about the fix on a problem where we actually need it. But that's kind of a easy thing to do. This gets real quick, real fast to do once you've done a couple of them. And let me just show you how fast you can do this thing. I need to get r sub x. I know to use cosine. I'm grabbing the numbers, 120 cosine 135 plus 65 cosine 55. Okay, and I wouldn't even really have to write that down because I could just grab the calculator and punch it in. 120 cosine 135. Please don't forget to close it off though. Plus 65 cosine 55. And I've already got my first number. That is a negative number. We have not seen that before. So something different is going to have to happen here. Negative 47 point. I already forgot what it was. 6, something like that. Okay? When I go to do step 2, the only thing different is I'm going to put a sign here and here. But the numbers are going to be the same. And there's a little trick you can play on the calculator. If I come in and go second equals, or second inner, it pulls that back up, and then I can use the arrow key to change that cosine to a sine. And go get this one, change that one to a sine. If you had more vectors, you'd have to keep going. But 138 will be fine there, I guess. R sub y is 138. I'm trying to keep about 3 significant figures on this. They gave me 2. You know, this has 2 significant figures. That has 3, 2, 2. So I'm kind of carrying 1 extra decimal, and then I'll probably round it at the end down to where it ought to be. But this was step 1, and here's step 2. They're already done. This is really easy once you get the hang of it. Step 3, you're going to take the 2 numbers you just got and run them through the Pythagorean theorem. And my suggestion here is to just leave the negative sign out. You're going to square it. It's going to be positive anyway. 47.6 squared plus 138 squared, and just run it like that. And I'll show you why here. But if I do second squared, 47.6 squared plus 138 squared, you hit enter. That thing has a magnitude of 146 meters, or 150 if you want to go down to 2, but I'll keep it at 3 here. Okay. If you turned, 120 at 135, we always measure off of the x-axis. So here's 0, here's 90 straight up, here's 180 over here, 270 would be straight down, and all the way back around the circle would be 360, like that. If I do 135 degrees, that's running right through the middle of this thing, right? Right there. So there's vector A, like that. Vector B is 65 at 55. So I kind of start over here, and I say, well, 0 is always horizontal to the right. There's my 0 angle line, just like this was, and I got to kind of restart, and I got to measure up from that 55 degrees, which puts me up here somewhere like that. And so vector B is going that way. All right. We want the resultant. So it's going to start down here where this thing started, and it's going to go up to the end point like that. I walked here, I walked here. The result is that I started there, ended up there. And it always goes from start to end. So there's no real surprise here. Okay? Why did that number come up negative? Because in the x direction, we ended up going a little bit to the left. And that opposite direction gets an opposite sign. It's negative. All right? Why did we get a positive number right here? Because we went up. Right? My y is up. If I were to plot this point right here like you did back in algebra class so long ago, you would write negative 47.6, 138 would be the coordinates of that point. You'd have a negative x and a positive y. So, but the length of the line would still be positive. All length is positive. So it's okay to leave that negative sign out. Now, what happens if you really want to put it in? Well, if you do it like this and you just put in the negative 47.6 and square that and add 138 squared, you're going to get the wrong number. All right? And you can see why. That negative right there, the squared happens first, and then it makes it negative. And I don't get 145, I get 129. I get the wrong number. What if they were both negative? All right? If I did negative 47 squared plus negative 138 squared, it's going to blow my calculator up. It's going to square 47, make it negative, square 138, make that negative, put those two negative numbers, get a big negative number, and then try to take the square root of a negative number. And I've got mine set to complex. Yours is probably going to blow up. And let me go down here and change it to real number system. When I do that, this is what your calculator is going to say, non-real answer. And it just says, I can't find a number that I can multiply by itself and give me a negative number. All right, there is a way to do it, clearly, but it involves those complex numbers. And we don't want to do that. We don't want a complex number. All right, so be careful with that one. Easiest thing in the world is just to leave the stupid negative sign out. all length is positive. The negative sign gives you a direction. All right, so I'm going to just put that as a little note right there to remind you. Step 4 was to get the angle, and here's where that new name phi comes in. If I do the arctangent of the second answer, the y component 138 over the x component 47.6, then I'll get that measurement. Second tangent 138 divided by 47.6 means that there is a 70.96, let's just call it a 71 degree angle. Somewhere there's a 70 degree angle. Okay, now if I'd put the negative sign in that, you see how I left it out again? If I had done it like it said, second tangent 138 divided by negative 47.6, I'd get a negative 71 degree angle. And so you could do it that way if you want, but the easiest way I know to do it is just to always leave the negative signs out of step 3 and 4, and then just know how to deal with it. You always get the same thing if you, down here, I would leave the negative signs out again, just because it makes it easiest. All right? And what you're going to get is one of 4, that 71 degrees could be one of 4 angles. It could be this one up here, right there. It could be this one right here. It could be this one right here. It could be the one that comes down this way. But they're all measured off of the x-axis because of the way I stacked arctangent there. And so that's what's happening there. I already know which one it is. I drew a picture of it. It's this one over here. I already know which one it is because it says go negative and then go positive. That means go left and up. And when I start here and go left and up, I end up with this one. This is the one that I want. And the 71 degree is actually over here, like that. That's not how we want to measure. We measure from 0 horizontal to the right. So what I need to do is to come back and say, well, I don't want the 71 degree angle. I want the angle over here, from 0 around to that. That would be the supplementary angle. And what I have to do is say, well, this would be 180 degrees and then subtract the 71. So this is that fix that got mentioned somewhere back there. The angle theta that I really want, I got to say 180 minus 71, and that would give me 109 degrees. That's the angle I want. This is the magnitude that I want. And I could come in here and write the resultant of these two vectors is a vector, and you need to go 146 somethings at an angle of 109 degrees, and that would be the answer that that we would want from that. All right, here's a little picture on how to know what to do with this thing. We said you're going to take the arctangent and call that the arctangent of r sub y over r sub x is going to give you this angle that we temporarily called phi. That will always be measured off of the x-axis, so it will be here, 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 or here. And arctangent honestly isn't smart enough to know which one of those it is. You have to figure that out. But it's easy to figure out, because if it's this guy, you're starting at the origin, this point right here in the center, and you're moving to the right and up. You'd have a positive x distance and a positive y. Everything in this quadrant of space over here, where that vector could lie, has coordinates positive, positive. Okay? If I end up over here in this quadrant, in this piece of space marked off by those two lines, then I would have to go left and up. I'd have to have a negative x and a positive y. Whereas down here I'd have a negative x and a negative y, and this would be a positive x and a negative y, like that. So when you look at the first two answers that you get, you know immediately which quadrant you're in. Let's go back to the last problem. You see how this was a negative number? That says x goes to the left. This one is a positive number. Y goes up. If I go left and up, perforce, I end up in the second quadrant. And we've already seen how to fix that. The angle that I want, quadrant 1, quadrant 2 is the one we're in now. Incidentally, these things get named because I start here at 0 and I go through the first quadrant. This is the first piece of space I'm in. Then, after I've rotated all the way through the first quadrant, I move through the second quadrant. And then down to the third quadrant. I'm doing Roman numerals. This would be quadrant 3 down here, and quadrant 4 right there. Okay, so quadrant 2, we just saw that theta, the angle I really want, is 180 minus phi, whatever I get out of arctangent here. All right, if this is a 30-degree angle, I'm 30 degrees shy of 180. I'd have to come over here 180 and back up 30, so I'd have 150. Quadrant 1's easy, because if this is a 30-degree angle, I want to start here at 0 and measure up. I don't have to do anything for this one. Just theta equals whatever I get out of arctangent. Quadrant 3, I need to do theta equals 180 plus phi. All right, I'd start here at 0. I'd rotate 90. I'd rotate the next 90, which gets me up to 180. And then I'd still have to do that 30 degrees right there. So this would be right there at 210. You can always check it. It's got to be between 180 and 270, but that would make sense. Quadrant 4, got a different fix for that one because I'm in a different piece of space. The angle that I want is 360 minus whatever arctangent slings me. So I start here and I go 0, go 90, 180. I'm rotating all the way around 270. Here's 360, and I back up 30 degrees. I'd be at 330. All right. So whichever quadrant you're in, you can find it pretty easily. You just got to look at the signs and figure out which quadrant you're in. From that, you always apply these same fixes, and it's okay. All right. I got one more of these things for you just to show you how to do the adjustment, but I think you can already see what's coming. I'm going to do this. It's already been almost an hour. I apologize for that. R sub x is going to be 80 cosine 235. You're welcome to break it into pieces. Stop it. Go get a sandwich. Come back later. Whatever you got to do. I didn't mean to go on that long. Something like that. Step 2 is going to be change your cosines to sines. Third one is going to be the Pythagorean theorem with the two numbers that you get right here. And the fourth step, I'll call phi first, would be the arctangent of those two answers. So let's go find those numbers and we'll fill it in here and see what we get. But you can see you could really just punch this straight onto the calculator and not even really write much of anything down. I want to do this right here. 80 cosine 235, close it up, plus 65 cosine 305, enters negative 8.6. So there's the answer to the first one right there. And I'll put a little circle or something around it. Step 2, I need to change these two cosines to sines. Second, enter. Step up here, hit sine. Step over here, get the other one. And I get a negative 118. Negative 119 maybe. Okay? So those are the numbers that I would put in here, except I like to leave the negative signs out. So that'd be 8.6 squared plus 119 squared. And just put it in the calculator that way. Then your calculator won't get mad at you. You're squaring those numbers. They're going to come up positive anyway. Square root 8.6 squared plus 119 squared. And that's 119.3. That 8.6 didn't move it very much. So I'm going to just put 119. We'll put the 0.3 just to make sure we know that's different. When I get right here, I need to take the arctangent of the second number over the first number. And again, leave the negative signs out. So 119 over 8.6 like that. Just leave the negative signs out on both of these. And that would look like this. Second tangent, 119 divided by 8.6 is 85.86. I'm going to go with an 86 right there just to make life easy. Maybe you want another digit in there, but I know I've got to fix that. How do I know? Because at least one of these had a negative sign, and I ended up somewhere else like that. Where did I end up? I got a negative x going to the left, and I got a negative y. I'm going down. If I go left and down, here's my resultant over here. That's in the third quadrant. Like that. And so when I found that this was an 86-degree angle, what I really need to do is to measure all the way around from over here, all the way until I get to the vector that I want. That's 180 degrees plus 86. And that would be, what, 266, I think. Okay, there's my magnitude. Here's my direction. Those are the numbers that I really want. And I come up here and I write R equals 86 at an angle of 266 degrees. Okay? And mercifully, that is the end of that. That's vector addition. There's some LOP questions. There's some lab questions. Get busy and do some of that stuff. Play with it. Get your head around it. It's not hard. You just got to do it a couple times. All right? Have a great day. Thanks so much, and be well.